Hi there, Mr. Sutton, bringing you the AB Calculus 4-8 Extra Practice number 5 solutions on mean value theorem. For this calculator-based free response problem, we're given a twice differentiable function f. We're told f prime of 2 is 0, and the second derivative, f double prime, is given by this crazy-looking quadratic exponential hybrid. Only between 0 and 6, though. So we want to know on what intervals between 0 and 6 the graph of f is concave down. Well, if I'm asking about concavity, especially concave down, I want to know where f double prime is negative. Let me start by figuring out where f double prime is 0, and I can do that on my calculator. So I'll start by putting f double prime as the y1 in my y equals, and then let me go to window, and let me make sure my window is from 0 to 6 because that's the interval they're asking about this on, and then let me do zoom 0, zoom fit, to get the perfect window of my function. And it looks like we're crossing only twice, right here and here. And we're negative before we cross and negative after that second crossing. So let me figure out what those x values are. Let me do second trace and then option 2, 0. And let me find, let's see, I have to move my spider a little bit to the left of that first intersection. So there we are, and press enter. Move a little bit to the right, press enter again, press enter one more time, and it looks like 0.464 is that first crossing. Now let me see what the second one is. So let me do second trace and then 0 again. And my spider begins the journey to the other x-intercept. A slow journey, but there we are. Let's press enter again, and a third time to get 5.357. All right, so we see here that f double prime is negative, which is what we care about, between 0 and 0.464, and also between 5.357 and 6. And it's probably negative in other places too, but that's the only thing we care about because they wanted on this interval, the intervals where we were concave down. And we haven't actually said we're concave down yet. This is the conditions for being concave down. Now we have to actually say f is concave down on these intervals. And now we're done. For this part of the problem, we want to know if f has a relative min, max, or neither at x equals 2. So there's a few ways you can test for this. One is by checking for sign changes in the first derivative. Can't really do that here because we don't know the first derivative. We do know that f prime of 2 equals 0, though. We do know we have a critical point. So if you know that much, you can use the second derivative to figure out if you have a max or a min. So that's what we're going to do here, is the second derivative test. Let's check out what f double prime of 2 comes out to on the calculator. So I'm back on my calculator. I quit out to the main screen. And to do f double prime of 2, I'm going to do, let's see, alpha trace and bring up my y menu. Y1 is where I stored f double prime. And let me plug 2 into that and press enter. Comes out to 3, apparently. Interesting. Well, the important thing about this is that 3 is a positive number. If the first derivative is 0 and the second derivative is positive, that tells us we have a relative min at x equals 2 by the second derivative test. For this part of the problem, they're asking us to use the mean value theorem on the interval from 2 to 4 to show that f prime of 4 cannot equal 8.5. So if we're going to use the mean value theorem for anything, we have to meet the conditions of the mean value theorem, which is that the thing that you're using the mean value theorem on, f prime in this case, has to be continuous and differentiable. Continuous on a closed interval, differentiable on the open interval. Now we know that this is the case. We know f prime is differentiable because they said that f was twice differentiable. So that means its derivative is also differentiable. Okay, so we've met the conditions for the mean value theorem. Now the conclusion of the mean value theorem, that's what's going to help us out here, is that if you are differentiable, that means that the average rate of change of the function, f prime, has to equal the instantaneous rate of change of f prime, which is f double prime, somewhere on the interval from 2 to 4. A rock has to equal I rock somewhere on there for some x value that we plug into f double prime. So let's say a little bit more about the average rate of change of f prime, because we can sort of figure it out based off of this value they're telling us f prime of 4 cannot equal. So if we were doing average rate of change for f prime over the interval from 2 to 4, we would say a rock equals f prime of 4 minus f prime of 2 all over 4 minus 2. So if f prime of 4 does equal 8.5, then a rock is going to look like 8.5 minus, well, they said f prime of 2 is 0 all over 4 minus 2. So this is 8.5 over 2, which is going to be 4.25. If f prime of 4 is 8.5, which they're saying we want to prove it isn't, but if it is, this is the average rate of change for f prime over this interval. By the mean value theorem, f double prime has to equal this, somewhere on the interval from 2 to 4, if the mean value theorem is going to be satisfied. So is this the case? To figure out if f double prime of c actually does equal 4.25 on this interval, probably the quickest way is just to graph the line y equals 4.25 on the calculator alongside f double prime and see if they intersect on this interval. Let's do it. So here I am, back in my y equals. I've entered 4.25 as my y2, and for my window, I'm going to make it precisely 2 to 4. And let me do zoom 0 again, zoom fit, so I can see both functions in their entirety on this interval. So there is my f double prime again, and there is the line 4.25. And let me just draw that out here. So we see here there are no points of intersection on the interval for these two functions here. Since f double prime of c does not equal 4.25 on this interval, it follows that f prime of 4 cannot actually be 8.5 after all. For this part of the problem, they want to know if f has a point of inflection at x equals 5, and then give a reason for the answer. So to see if we have a point of inflection, it might help to see if f double prime equals 0 or undefined at x equals 5. That's not proof that we have a point of inflection, because you still need to show that there's a sign change in f double prime for a point of inflection, but it's at least a good start. So if we do f double prime of 5, let's do that on the calculator and see what we get. So on the calculator, I'm going to do alpha trace to pull up this y1 here, open parentheses and put 5 in there. I stored f double prime as y1 in my y equals, so this is a quick way to just plug in 5 to that. And if I press enter, f double prime of 5 appears to be about 0.245. Okay, well, that's not 0, and it certainly is not undefined. It's definitely defined. So it appears we do not even have a critical point for f double prime at x equals 5. Since we don't even have that much, I mean, forget about a sign change, we don't even have a critical point to change signs around, therefore f does not have a point of inflection at x equals 5. On this no calculator based problem, we're given f that's a twice differentiable function. We were told f of 2 is 5 and f of 5 is 2. That's kind of interesting. And g is this other function that's f of x. All right, so that's the backstory. For the first part on this, they want us to explain why there has to be a c value between 2 and 5 where the derivative is -1. So if you're trying to give guarantee a certain derivative value, a certain slope value, and you have some information about the original function, the mean value theorem is kind of our go-to in this situation. To use the mean value theorem, we first have to establish that our function is differentiable on the interval in question. And they said that f was not just differentiable, but twice differentiable. Therefore, we have the differentiability on all real numbers, so certainly that includes the interval from 2 to 5, and we can go ahead and use the mean value theorem. Now, if you have differentiability, mean value theorem says the average rate of change of this function on this interval is going to equal the instantaneous rate of change somewhere on the interval. So we just need to find the average rate of change and show that it equals -1. For average rate of change, we're going to do f of 5 minus f of 2 over 5 minus 2. So that's going to be 2 minus 5 over 5 minus 2. And let's see here, that's -3 over +3, which comes out to -1. Well, that's exactly the instantaneous rate of change we were looking for. Since we've shown that the AROC matches this number here, that means by the mean value theorem, f prime of c must equal -1 somewhere on the interval from 2 to 5. For this part, we're being asked to show that g prime of 2 equals g prime of 5, and then use that to explain why there's some k value where g double prime equals 0 on the interval from 2 to 5. All right, so one thing at a time. Let's do this first part here. So for figuring out g prime of 2 or 5, we need to know g prime of x in general. That's going to require a chain rule here. So we're going to take the derivative of the outer function. So we have f of something is the outer function. So its derivative is going to be f prime of something, in this case f prime of f of x. But now we have to multiply by the derivative of the inner function. So we have a tail of f prime of x. And this is what g prime ends up doing. So g prime of 2 then is going to be f prime of f of 2 times f prime of 2. And we know that f of 2 at the very least is 5. So this is really f prime of 5 times f prime of 2. Unfortunately, we don't really know what f prime of anything is. So we're going to have to leave it like this and hope for the best. Let's take a look at g prime of 5 and see what that generates. So that's going to be f prime of f of 5 times f prime of 5. Now f prime, or f of 5, just f of 5, looking up here, has a value of 2. So this expression is really f prime of 2 times f prime of 5. And this is pretty much just multiplied in a different order, the exact same thing that we saw that g prime of 2 equaled. Well, since g prime of 2 equals this, and g prime of 5 equals this, and these things are really the same, that means that g prime of 5 in the end does actually equal g prime of 2. We still don't know what exactly that value is, but we know that they equal each other. All right, so here's why this is important. So we're supposed to use this result to explain why there's a k value between 2 and 5 where g double prime of k equals 0. So we know a little bit about g prime. We're trying to guarantee values of g double prime. Again, we're going to go to the mean value theorem to figure this out. To use the mean value theorem, we must again show that we have differentiability, this time for the g prime function. How do we know that g prime is differentiable on the interval from 2 to 5? Well, they told us that f was twice differentiable. And g prime is made up of both f's and f primes. So if everything that g prime is made up of is differentiable, and we're just multiplying here, it's not like we're dividing by anything, then that means that g prime itself must be differentiable. All right, well, given that, let's take a look. If we're trying to guarantee an instantaneous rate of change value for g double prime, we need to take a look at the average rate of change for g prime. So we're going to have g prime of 5 minus g prime of 2 over 5 minus 2. This is, again, a rock for g prime. And this has a value of, well, let's see here. If g prime, we don't know what g prime of 5 is or g prime of 2, but we do know that they equal each other. This means that when we subtract them, we must get a value of 0. So this average rate of change comes out to 0 over 3, which is to say 0. Since the average rate of change of g prime equals 0 on the interval from 2 to 5, and we have a differentiable function, that means that the instantaneous rate of change of g prime, namely g double prime, must also equal 0 for some k value on 2 to 5. And again, this is guaranteed by the mean value theorem. For this next problem part, they want us to show that if f double prime of x is 0 for all x, then the graph of g doesn't have a point of inflection. So maybe it would help if we knew what g double prime was doing, because points of inflection, we show that we do have those by showing a sign change in g double prime. In order to get g double prime, I have to take the derivative of g prime. Recall from part B, g prime was really f prime of f of x times f prime of x, just application of the chain rule. So g double prime then is going to require the product rule since we have two things being multiplied. So that's going to be u prime v plus uv prime in general. Let me set up a box and ribbon to help me organize this. So my two factors, I've got f prime of f of x and just plain old f prime of x. The derivatives of these, well, this first one's going to require the chain rule. This is going to be the derivative of the outer function. The outer function's f prime of something. So this derivative is going to be f double prime of something times the derivative of the something times f prime of x. So that is this derivative. And now over here, derivative of f prime of x is just going to be f double prime of x. Multiplying these out using the ribbon, this is going to be fun to say. I have f double prime of f of x times f prime of x times f prime of x. So I guess we could say f prime of x squared just to make it look a little bit cleaner. And then we're going to be adding f prime of f of x times f double prime of x. Now, going back to the original problem here, they said, show that if f double prime of x equals 0 for all x, then we don't have a point of inflection. Well, what happens to all this if f double prime equals 0? If that's the case, then we can rewrite this as 0 times f prime of x squared plus f prime of x times f of x times 0. Well, this first term is going to be 0. This second term is going to be 0, so the whole thing comes out to 0. And that's a problem if you're looking for points of inflection. If g double prime of x is also always 0, then that means g double prime of x cannot change sign. And if you don't have any sign change in the second derivative, you can't have any points of inflection for the original function. On this problem part, we're defining a new function, h of x, as f of x minus x. And they want us to explain why there has to be some r value between 2 and 5 where h of r is 0. So if we're trying to guarantee certain outputs from the original function on an interval, generally that's going to be the intermediate value theorem that we want to use. To use the IVT, we have to first demonstrate that we have a continuous function on the closed interval, and we also have to show that the beginning and ending output values sandwich the value we're looking for. So let's start with the continuity piece. H of x is made up of f of x minus x. Now we know that f is twice differentiable. Since f is differentiable, it is also a continuous function, and since f is continuous and x is continuous, having two continuous things being subtracted is going to give you another continuous function. H of x, therefore, is also continuous. Now we have to show that h of 2 and h of 5, we're going to have to show that 0 is between those two values. So let's take a look at h of 2. That's going to be f of 2 minus 2. Now f of 2 they gave us, that's 5, so that's 5 minus 2, which is going to be 3. Let's take a look now at h of 5. That's going to be f of 5 minus 5. They showed us f of 5 up here was 2, so this is 2 minus 5, which is negative 3. Is 0 between 3 and negative 3? It is. Negative 3, less than 0, less than 3. Therefore, by the intermediate value theorem, there is an r between 2 and 5 such that h of r equals 0.